All right, so overall, really fantastic job on the midterm. This was one of the more challenging exams I've given for a midterm in 222, and I decided to raise the bar and leave more room for people to sort of, be assessed, and people just nailed this. Okay, so the last question was challenging. I expected the last question to be challenging with reversing the list. I put that in there to give you a chance to do something using what you've done, but thinking about stuff in a new way. So if that question was extremely challenging for you, don't panic over that, okay? Testing is inherently kind of artificial. You don't usually go on the job and have a 50-minute time limit where you're not allowed to look at any resources or talk to anybody else. It's artificial, but it's what we do to assess, is give tests. But the other questions, right, were basically, fundamental linked list stuff. Working with pointers, dereferencing pointers, and thinking about, how structures in memory work and how you can relate changes to memory with code. And I think everybody is pretty much on top of that. So I think as a halfway point, we're like exactly where we should be or better at this stage. And so, I mean, if your overall grade was 60s on this, that is definitely still passing, okay? Because it was an ambitious exam. So don't panic over the grades, but if you feel like you're not sure what was supposed to happen on here, or you feel lucky that you got some of the answers right and stuff, definitely come and talk to me. But let's go through the details of this. Assuming I can remember which midterm this was. Okay, this sounds good. All right, so question 1 was playing with structures. And had a few pieces. First part was to, there was a typo in here, so I said consider a structure named node, and I asked you to make a structure named data. And most people didn't notice the typo, including me, and I just went ahead and made a structure named data. But there was some confusion in there if you saw that. So some people made a structure named node and then type-defed it to the word data and such. So I started off taking off points, and I went back and changed that. So if there was confusion like that, I gave you credit for it. What I was really looking for was can you declare these types of things in a structure statement? So, keyword struct, name of the structure you're defining, let's suppose it's data. And then, so a string named name with no predefined maximum length. You can't say character name bracket 10, because that says it can only hold 10. The only way that you can define a string without specifying the length is to use this star notation. So it's character, bless you, star name. Single integer, or single character is just a car. The name was my car. Single integer named val, and an array of 10 integers named numbers. So integer, name of the variable, and then in bracket you list how many things you want in that array. So if you want an array of 10 integers, this is a 10. Okay, the last index of the integer will be bracket 9 because we start from 0. But if I say integer numbers bracket 9, I only have an array of 9 integers. If I say bracket 11, I have an array of 11 integers. Now, one confusion is when we deal with strings, if we want a string that holds 5 characters, we actually need an array that holds 6 characters because we need to put the null terminator on the end. But in general, for an array, if you want 5 numbers, make it an array of 5. And the bracket 10 goes after this. If you're in Java, it goes after the int sometimes, but I didn't take off for that. And you don't need to define a struct node star named next, right? There's nothing in this structure that should say struct node star next, so I actually took off a point if you did that. Right, if we need a field name next that points to another struct data, then we would say struct data star next. But it's not always a part of a structure, and it's usually not. All right, so that's part A. Part B, write a statement declaring a variable named code to have type struct data star. So most people did something like this. Struct data star code. Okay, this is really the type of variable, and this is a variable. And this is a variable declaration, okay? This is defining a structure, this is declaring a variable named code. It's not giving it a value, it's just declaring it to say, code is a pointer to a struct data. So part C, I wanted to allocate a chunk of memory and make code equal to that. So write a malloc statement to set code variable to point to a block of memory large enough to contain a struct data. So code equals malloc. And I asked you to use a size of statement because you don't want to just say pointer, character, integer, 10 integers and add those up, because there's padding that goes in and stuff. So size of, we'll tell it to calculate how big this structure is. And I don't think anybody did a struct data star, which is great. So that's how big a struct data is, allocate that much memory, set code equal to that address. And then the last part, we're just doing some initializations. And the one trick here is how to set up name. So name is a pointer to a character. Okay, so this is legal. If you do name equals double quote Sally, that's legal, that'll work. Okay. When you say double quote string in C, the compiler will find a chunk of memory big enough to hold that string plus a null terminator. It will load the characters SALLY and a null terminator into that location of memory. And then this double quote Sally will basically be the address where that S was stored. So if I say name equals quote Sally, this variable right here, which is a pointer, will be the address in memory where that S is stored. And you're guaranteed the next spot in memory has an ALLY and a null terminator. So if you just want to make name equal to Sally, that's all you need. Okay, but there's some details. For example, you can't always change this later on. If I try to change name bracket 0, I may get a seg fault. So if you want this to be totally general purpose, you can go with string copy. And this is a little nod to what you're doing in PA3. But if I just say string copy name quote Sally, that's going to be another seg fault. Because I've declared name, but I haven't initialized it. I haven't told name where it points. So name is probably equal to 0, and I'm trying to copy into memory location 0. That's a seg fault. So you need to point somewhere reasonable. And I need to allocate some space. Well, if I'm storing the word Sally and I want a null terminator, I could just malloc 6 bytes. Or I could do 6 times size of character. Or I could do 1 plus string length of Sally times size of character if I wanted to be totally general. But all of those will just be 6. And this is what you're doing in PA3 when you load a license plate in, right? Whatever the length of your license plate is, got to add 1 to it for the null terminator, and then use that as an argument to malloc to make space that you can string copy into. And when you're doing these assignments, This is going to be, for example, code arrow name up here and up here, or up here, or to set value equal to 0, it will be code arrow value equals 0, and so on. To code the pointer, you need to dereference it, find the thing it points to, and pick off the different fields. That's what the arrow notation does. All right, question 2, you had this funny looking node structure with a time, a temperature, a name, and a pointer to a next node. The list has a sentinel, you're past the address of the sentinel, and you're supposed to count, you're supposed to calculate the sum of all the temp values in the list. So, issues here. All right, first issue, you really don't need to do any mallocs here. Use malloc if you're trying to create a new node. There's nothing in here that requires you to create a new node. You want some temporary variables to point to nodes, right? But you're pointing to things that already exist. Here's your list. Here's a node. Here's another here. Here's another node. You might want a temporary variable to point to these and move through the list, but you're not actually creating new stuff in memory. You're just making new variables that point to things that are already there. That tells you don't use malloc. Okay. If you used malloc, chances are after you used malloc and you set temp equal to malloc, you change temp to be equal to sentinel or sentinel next. That's a memory leak. Right? And then later on, if you free sentinel, now you're destroying your list because you've just taken the head of the list and thrown it back into the memory pool. Similarly, you don't always need a previous and current or a current and next. Right? We need a pair of pointers if we're trying to move through our list and keep track of the spot before where we are so we can delete or insert. But in general, you don't need that. In your print routine, for example, you usually just have a single pointer that just moves through the list. Right? If you can do what you need to do at each node and then move on and never have to look back, you don't need a pair of pointers. So some of the solutions for this were longer than they probably needed to be. Which is okay, right, except if you're time constrained, shorter is usually better for you. So let's make a count function. Okay, so sent is a sentinel. Most people are working these edge cases really well as far as making sure you start with the first node, making sure you process the last node, and then don't go beyond that. Most people are doing that well. Doing it in different ways from one to another, but doing it successfully, which is the key. So here's how I do this, right? I start off looking at the first data node, or possibly null if the list is empty. So struct node temp is a temporary. That's the node the sentinel points to. And then I'm going to iterate while that's something. So while it's not null, I'm going to have a running sum, so I'll initialize that. Declare it as an int. And then I want to add the temperature field of this node, so that's the unfortunately named temp arrow temp. And then just return your sum. If you start off with temp equal to sentinel, you can loop while temp next is not null, and then add temp next temp to your sum, and don't forget to move down the list. The real key is whatever your while condition is should guarantee that these will not throw seg faults. Okay, that's a quick check. If I do this while temp is not null, and I try to do something with temp next arrow something, right? Temp next could be null, that could be a seg fault. So that can help keep things straight. So most people seem to be doing that. What you don't want to do is, initialize your sum inside your while loop, because your sum will always be, reset to 0. So don't do that. Don't do any freeze unless you do mallocs, and you don't need to use any mallocs. Make sure you don't count the sentinel node. So start either by skipping over it or, look one ahead inside your while loop. Always, always, always use null. Don't ever use a 0 there. Okay, that'll get you dinged like major points on the job or in interviews and stuff. Always use null. Okay, null is set up in standard io.h to be whatever the magic value is that malloc gives you when it's out of memory, and that you can use safely as a flag, and so on and so forth. And today, null is synonymous with 0, but go back 30 years, not the case. Right? Memory location 0 would be perfectly valid on some machines. So always use null. All right, so the next one was some analysis and list manipulation. So there's a linked list. What gets printed out by this? And you can draw a picture if you're not changing things. If this node is LL, then this is LL next. This is LL next next. And so LL next next data is that node's data, and LL next data is that node's data. This will just print 10 followed by -1. If I'd add LL next 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 data, that would be my 50. And if I just do LL data, that's my 42, the sentinel node's data. All right, delete the last node without using any loops or conditional statements. A few ways to do this. So we want to delete this 50. Well, you can use temporary variables, right? So -1 equals LL next. Node 10 equals -1 next. Node 50 equals node 10 next. Right, so I can set up names for each of these. I'm calling this node -1, node 10, node 50. This is LL. Well, once you have names for each of these, once you have, declare them to be struct node stars, then this is pretty straightforward. How do you delete node 50? Well, just set node 10's next to be null. So n10 next equals null, and then free node 50. So that gets you there without having to do too much deep thinking. Right, we're just putting labels on the different nodes. If you want to take it the other extreme, so LL next, next, next. That's the address of node 50. We can free that. And we can do that right up front because we don't need to use any information from this node after we free it. What we need to do is set this field to be null, which is just LL next, next, next equals null. That sets up this field to say don't point to anything. And if you think about this quickly, it looks weird. because I'm freeing LL next, 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 and now I'm using LL next, next, next and setting it equal to something, right? Two different things going on here. When I say free, I'm passing the address of node 50, right? I'm actually passing the value that's stored in here and saying free what that points to, which frees this block. And now I'm just changing the value of this entry, this field in node 10. But if I switch these, that's not going to work. If I switch these and I change this to be null, and then I say free LL next, 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 I'm going to try to free null. That's going to seg fault. Here's another thing that doesn't work. So I can set last pointer equal to LL next, next, next. So last pointer is equal to whatever is stored in here. Okay, and I can say free last pointer, and that will free this block of memory. So far, so good. Here's what won't do what you'd like it to do. Last pointer equals null. That does not change the contents of this, right? Last pointer is a local variable that I declared to be a struct node star. I've changed it from the contents of this to just being equal to null. But that doesn't actually change what's in this field. To change what's in that field, I have to do something like, pointer equals LL next, next. So that pointer is this node right down here, and then I can say pointer next equals null. Right, that will work. So it's a subtle but important difference, right? This is just setting something to be a location in memory, and now I'm setting that location in memory to be null. I'm not changing anything else in memory except this variable. Here I'm pointing to a node, and here I'm setting a field of that node to be null. That's actually changing the contents of that lower piece of that node. All right. I tried to make this clear and it came out confusing. Write some C code to create a new node with a data value of 5 and a variable named new that points to that node. And I was trying to make it clearer and I made it more confusing. So here's what I was envisioning. Write some C code to create a new node with a data value of 5. So and make a variable named new. So struct node star new equals malloc size of struct node, and then new data equals 5. Right? And now new is a variable that points to this node that you just created with malloc, and you've set it equal to 5. But some people interpret this to mean that I wanted a node whose next field was equal to new, and so they created 2 nodes and set the second one to be 5 and the first one to point to it, and so on. So if that was going on, I gave you credit for it, but I wasn't trying to be tricky here. So I just wanted a node. And then part D was to insert that new node between the -1 and 10 in the original list. And so -1 is here and 10 is there, and you want to sandwich new in between those. And well, if you do M1 equals LL next and N10 equals M1 arrow next, right, the setup is pretty straightforward. M1 next equals new, and new next equals node 10. So that'll do it. If you didn't use temporary variables, you can still do this pretty easily. You have to set up new first if you're not using a temporary. So we want new to point to this node N10, which is LL next, next. In other words, the value that's in this field, that's what we want new to point to. So new is pointing to node 10, and then LL next, next is equal to new. So that field points to our new node. So new gets sandwiched in between the two. All right, question 4, swapping nodes. And most people nailed this too. And I didn't want you to swap data values, right? Don't just copy the data value from here to there and swap them. I wanted to actually swap the nodes. So to swap 2 and 3, you've got some node over here. Basically, you need node temp 1 to point to temp 3, temp 3 to point to temp 2, and then temp 2 to point to whatever this next node is. So it's 3 assignment statements. And the order is a little bit relevant. Let's do temp 1 first because we're not changing what points to temp 1. So temp 1 next. Well, we want it to point to temp 3. And then temp 3 next should point to temp 2. And then temp 2 should point, it should take the place over here, it should point wherever temp 3 was pointing. So I want to do that before I change temp 3 next. So I'm going to do temp 2 next equals temp 3 next. So how do you check this? So let's pretend that's our list, 10, 20, 30, and this is pointing to 40. So temp 1 next equals temp 3. That's going to look like that. Temp 2 next equals temp 3 next. Well, temp 3 next is right here, so temp 2 next is going to go here. That's that statement. And then temp 3 next equals temp 2, so this is going to point to temp 2. And now follow your nodes, see how we did. We started here, we went to this node, that leads us to temp 2, and that leads us to the 40, and after that everything should be the same. Everything before the 10 should be the same. So you can sort of sanity check. All right, and then the list reversal. So one key here was I wanted to create a new linked list, okay, containing the nodes in reverse order. So you don't want to change the original list and swap things around. And if I try to reuse the nodes from the original linked list to make a new linked list, I'm going to have to modify the pointers in there, right? And that's destroying the original list. And I had a note on the board, don't change the original list. So you got to make a new list. And I had a algorithm here you could follow if you wanted, which would start with an empty sentinel node, read the first node from the old list, stick it in the beginning of the new list, and just keep doing that. Move to the next node of the old, put that in the beginning of the new, and so on and so forth. And when you're done with the original, you're done making the reversed. So take a sentinel and let's create a reverse list. So so make a new sentinel node. Have it point to null. So new is our outgoing list. It's the reverse of the one we're starting with. Struct node star temp. So I'll initialize struct node star temp to be what the sentinel's pointing to. That's my first data node, or null, right? I do this like a million times up to this point in the course. Iterate on temp. Okay, if temp is not null, it is the first data node of the original list, so we need to make a corresponding data node to put in our new list. So struct node star, node equals malloc, whatever. Copy the data. So I've made a new node for my reverse list. I've copied the data value into the data field. Now I want to insert it into the beginning of my new list, right? Because if I'm reading from beginning to end and I'm always inserting the beginning, my new list will come out in reverse order. That's the hint of that algorithm. So, so insert at the beginning. Well, our new list, the sentinel is called new. So node next equals new next, and then new next equals node. So we're trying to insert a node into the beginning of our list after new. So have node point where our sentinel is pointing, and then have our sentinel point to node. That squeezes this into the beginning. Move down the list. And when you get to the end of that, your temp is equal to null. You hit the end of the list. The last node that you put in your new list, you would have set to point to new next, which would have been null. And then just return the sentinel of the reverse list. So some people assume that there was at least one node in the list, and I gave you credit for that. But you need to deal with the possibility that there's just a sentinel node and there's no data nodes, in which case, what do you return? You return a sentinel node of an empty list. Okay, can't be the same sentinel node you started with, because now you got two sentinels for the same list. And if you start adding something to this reverse list, you're going to modify the original. So this will still work if your list is completely empty. If it's just a sentinel, you'll end up returning just the new sentinel and nothing else. You got to be doing some mallocs. And you've got to link your new nodes together into an original list. Minor edge cases, missing the last node, that kind of thing, not a big deal. Some people printed out error messages if it was an empty list. Normally I would ding you a bunch for that, but I didn't. But there's nothing in here that says you should print anything under any circumstances. And in general, when you're writing code, unless the code spec says to print something, don't ever print something. Okay, that's like a major disruption to whoever is using the code, because they might call your code 1,000,000 times expecting that it might throw an error condition, and they'll just deal with it in the return value. And if your code starts printing 1,000,000 error messages, right, it's going to freak people out. So don't print unless you're told to, particularly in functions. All right, questions on any or all of that? So general note, this is from 224 also, right? If it says write a function, you got to write a function, okay? If it says write some C code, right? It doesn't necessarily have to be a function. I'm just looking for some lines of code that will do this. You can write a function called swap nodes and have it take in, you know, a struct node star, although I didn't give you a name of the list here, right? But if you just want some C code, just write some C code, okay? Or if you're not sure, ask. If it says write a program, which none of these did, then you need a main program. It's got to be called main, and you want to include standard I/O if you're doing I/O and all that sort of stuff. This was just some C code, and this was a function. And then one was just some short answer C code. All right, so come and talk to me if you want to go over any of this. My office hours tomorrow are reduced because I have a CS meeting to go to at 8, but I'll be in at 7:30. And my other hours this week are as usual, including today at 12 o'clock. All right, so I will plan on talking tomorrow about PA3. I want to talk about the main program for PA3 because there may be some confusion about that. And then we'll go on and we'll talk about queues to round out talking about stacks. All right, so I'll see you next time.